شرمنده از اینکه طولانی شدش و خب فقط اولا که ممنون که دعوتم کردیم و نمیدونم بیشتر بچهای ریاضی هستید یا فیزیک، ولی این تاک بیشتر فکر کنم فیزیک هستش تا ریاضی، مقدار فیزیکش بیشتره، با اینکه من خودم خب شریف که بودم ریاضی خوندم و پیشم ریاضی بوده، ولی کارم بیشتر الان فیزیک و تاکم که امروز میدم بیشتر مربوط به کارهای اخیرمونه که همین مبحث کامپیوتر کوانتومی و مدارهای ابررسانا مربوط میشه. بعد خب من خیلی وقت به فارسی چیز ندادم تا که صحبتی ندادم، بر همین احتمالاً میتونم سعی کنم فارسی شروع کنم، ولی ممکنه از یه جا بعد ببینم که پیش نمیره و مجبورم به انگلیسی سویچ کنم و همون فارسی ها احتمالاً کلمه‌هایی که استفاده خواهم کرد بیشترشون به انگلیسی خواهد بود، چون خیلی رو نمیدونم فارسیشون و برای همین خب عذرخواهی میکنم از پیش. خب من خودم اول معرفی کنم. من توی اینریای پاریس که الان اینجا هستش که هستم محقق هستم و توی دانشگاه پلی‌تکنیک استاد پلی‌تکنیک پاریس و در اینریا در واقع من یک گروهی رو مدیریت میکنم به اسم گروه کوانتیک که گروه مشترکی است با دو تا دانشگاه دیگه، اکول دمین پاریس و مدرسه اکول نورمال پاریس، که یه دونه گروه بین با یک سری فیزیکدان تجربی و یک سری ریاضیدان کاربردی. یک سری نصف هستیم، نصفمون ریاضیدانن، نصفمون فیزیکدان تجربی هم کارهای اکسپریمنتال انجام میدن. این عکسایی هم که همین صفحه اول گذاشتم یه سری عکس از لابراتوار خودمونه که توش آزمایش انجام میشه و حالا در موردشون خورده بیشتر صحبت میکنم در طول این سخنرانی. این چیزی که سمت راست میبینید یه دیلوشن کرایستاپ هستش، یه دونه یخچاله که خیلی خیلی دمای پایین میتونه برسونه. در واقع مدارهایی که ما استفاده میکنیم برای اینکه این کامپیوتر کنترل میسازیم مداری مثل این چیزی که توی سمت چپ میبینید که مدار ابررسانا هستش که در موردشون یه خورده بیشتر صحبت میکنم بعداً. مدارهایی هستن که معمولا از جنس آلومینیوم یا ابررسانایی خیلی خوب هستش استفاده میشن روی چیپ سیلیسیوم یا سافایر. و این دستگاهی که در سمت راست میبینید اجازه ما این در واقع مدار رو در این سیلندرهای، این استوانهایی که این پای میبینید یه جوری جاسازی میکنیم و این دمای اونا رو به تقریبا 20 میلی کلوین یعنی 20000 درجه بالای صفر مطلق میرسونه، که در واقع نه تنها کافیه برای اینکه این آلومینیوم خواص ابررسانایی از خودش نشون بده، بلکه میتونه باعث میشه که ما در واقع به یه رژیمی برسیم که میشه رژیم کوانتومی. در واقع قوانینی که ولتاژ رو کارنت در این مدار ما براشون حاکم میشه دیگه قوانین فیزیک کلاسیک نیست، دیگه قوانین الکترونیک کلاسیک نیست، قوانین فیزیک کوانتوم. و از این سعی میکنیم در واقع یه دونه کامپیوتر کوانتومی بسازیم یا قطعات یک کامپیوتر کوانتومی بسازیم. و در واقع الیمنت پایه در واقع این کامپیوتر یا این در واقع مدارها، چیزی که رول در واقع ترانزیستور رو برای ما بازی میکنه، یه چیزی به اسم جوزفسون جانکشن که یک در واقع یک چیزی مثلا یه اینداکتنس یا القاگر فکر کنم میگفتیم، القاگر غیر خطی ابررسان است. در موردش خورده دیرتر صحبت کنم. خب تو ممکنه که همینطور در مورد شنیده باشید، ولی امروز در مورد کاربردهای زیادی از فیزیک کوانتوم برای در واقع تکنولوژی جدید صحبت میشه. از کامپیوتر کوانتومی که صحبت حتما شنیدید، مثلا کمپانی بزرگی مثل گوگل و آی بی ام دارن خیلی روش سرمایه گذاری میکنن و موضوع همین سخنرانی هم هست. ولی علاوه بر کامپیوتر کوانتومی، کامیونیکیشن کوانتومی، مخابرات کوانتومی، یک کاربرد دیگه هستش که در اینجا بیشتر بحث امنیت ارتباطات که در واقع با ذخیره کردن اطلاعات در حالت کوانتومی نور ما میتونیم با استفاده از این خاصیت فیزیک کوانتوم که در واقع با اندازه‌گیری حالت یک اندازه‌گیری ذره یا یک موج در واقع شما اون حالت اون ذره و موج رو تغییر میدید، میتونیم یه جوری با امنیت این مخابرات ارتباطات رو در واقع انشور کنیم. در کاربرد بعدی که میتونیم بهش فکر کنیم کاربرد مترولوژی کوانتومی هستش یا اندازه‌گیری دقیق کوانتومی. مثالی که همیشه مطرح میشه لایگو هست که یه دونه اینترفرومتر در واقع برای اندازه‌گیری امواج گرانشی. چند سال پیش شنیدید که تونستن اولین بار امواج گرانشی رو ثبت کنن توسط همین لایگو و امروز سعی می‌کنیم با استفاده از همین حالت‌های کوانتومی نور در واقع دقت این اینترفرومتر رو بالاتر ببریم. و بعد از این یک سری ماشین‌های دیگه هم هستن که من همه رو کاتگورایز کردم تو ماشین‌های کوانتومی دیگر. بیشتر در واقع میشه اینا رو ماشین‌های کوانتومی یا پروسسورهای کوانتومی دید که یک کار خیلی خاص انجام میدن. شما همونطوری که شاید بدونید اولین کامپیوترهایی که به وجود اومدن کامپیوترهایی بودن که در واقع میتونستن یک مسئله خاصی رو سیمولیت کنن، شبیه سازی کنن یا یک محاسبه خیلی خاصی رو انجام بدن. کامپیوترهای در واقع برنامه قول معروف یونیورسال نبودن که بهشون روش برنامه‌ریزی کرد که هر جور مسئله حل کنه و این جور ماشین‌هاش بیشتر ماشین‌هایش در واقع همچین کاری رو میکنن. یک سری با یه مدار کوانتومی خاص ما میتونیم یه ماده خاصی و یک چیز یه فرآیند شیمیایی خاص رو به طور مثلا شبیه سازی کنیم، یک مسئله خاصی رو اپتیمایز کنیم، بهینه کنیم. خب اینا همشون کاربردهای مختلفی هست که این روزا محققا دارن روشون کار میکنن، ولی تو همه اینا یه مشترک اینه که چه چیزی در واقع از لحاظ ریاضی اگه بخوایم بگیم چه چیز خاصی هستش که فیزیک کوانتوم رو تغییر میده نسبت به فیزیک کلاسیک و باعث میشه یک سری قابلیت‌های جدید داشته باشیم. به نظر من تو این سه تا در واقع سه تا موضوعی که اینجا هستش، سه تا در واقع موضوع پایه‌ای هستن که در واقع چیز میکنند. ببخشید فکر میکنم من بهتر باشه که به انگلیسی حرف بزنم خیلی اگه اشکالی نداره براتون. اوکی
بفرمایید.
So I'm going to switch to English. There are three main features that basically let us that differentiate quantum mechanics from classical mechanics and give us all these new capabilities that we didn't have. And so these three capabilities are first, these features are that first that in order to model basically an isolated quantum system, instead of using the laws of Newton, as you know, we use the Schrödinger equation. So basically, an isolated quantum system which doesn't interact with its environment can be modeled by what we call a wave function, which lives in a Hilbert space and which satisfies this equation. So you have I, which is square root of -1, h bar, which is the Planck constant, d over dt of psi equals to h psi, where h here is a Hamiltonian, which is an operator, a Hermitian operator, defined on this Hilbert space. Okay, so because H is a Hermitian, it's a self-adjoint operator. Basically, what you can show is that the norm of psi is conserved. Basically, psi lives on the unit sphere of this Hilbert space, and that's the first feature in quantum mechanics with respect to classical mechanics. Just the fact that the Schrödinger equation replaces Newton's laws. The second feature is the fact that when we want to model composite systems, for example, a system which is given by an interaction of two systems S and M, we can do it only by using a tensor product of the two systems and not by a Cartesian product, as in the case of a classical system. So basically, the new system is now defined in the Hilbert space, which is given by the tensor product of the two Hilbert spaces, Hs and Hm, of the two systems. And the Hamiltonian of the system is then of this general form. So Hs tensor Im. So basically, you have either Hamiltonians which act only on the S part of your system and not on the M part. Hamiltonians which act only on the M part and not on the S part. Basically, identity on the system, on the S part. And then some maybe interaction Hamiltonian which couples them together. So why is this important? This is actually the main feature which gives all the force of quantum computation. This is just saying to you that the dimensions of composite quantum systems increases exponentially, basically, because each time you add a new system, you multiply the dimension by the dimension of the new system. You see, because you have the tensor product of these Hilbert spaces. If this system is, let's say, m-dimensional, or s-dimensional, this is m-dimensional, then the dimension of this system is s times m. Whereas if you had it in the, you were in the classical case, and you had a Cartesian product, so the dimension would have been s plus m. So you can increase the dimensionality of your space, information space, basically very rapidly by increasing the number of parts in your system. Okay. And so this is also very related to the concept of entanglement. What it means is that basically for this system, composite system S and M, we cannot talk about the state of S independently of the state of M, because as you will see, in the tensor product, basically you can have the state of the first. Basically, these two states are going to be codependent. So we're going to see it maybe in a bit in the next slide, actually. Okay, so the third property, which for the case of quantum computation is actually a hassle, it's not helping us, but for the case of quantum communication is actually the essence of quantum communication, why you have security, is that it's the concept of measurement. When you want to measure a quantum system, basically you have these two features which change everything with respect to classical case. You have first the randomness and then the irreversibility of the results basically what does this mean? It means that so first of all, how do we explain a measurement in a quantum system? So if you want to any observable or any quantity, physical quantity, if you want, like position, momentum, or energy, you can associate an observable, which is an operator, a Hermitian operator again, a self-adjoint operator on your Hilbert space. So as it's Hermitian, you can decompose it, you can diagonalize it if you want, and you can write it in this form, basically in the form of this spectral decomposition of sum of lambda mu's, where lambda mu's are the eigenvalues, and p mu, where p mu is the projection operator over the eigenspace associated to the lambda mu. Okay, so to any physical quantity, we can associate an operator of this form, and then the quantum mechanics tells us that if each time you want to measure this observable O, you're gonna necessarily obtain one of these values lambda mu, which are the eigenvalues of O. But which one you're gonna measure, you're gonna obtain as the measurement result, that's gonna be a random result. And the probability of measuring, for example, lambda mu is given by this value. So first get this projection operator, apply it to the psi, the state of your system, and then take the scalar product of this vector or this wave function with psi itself. So Hermitian product of psi with p mu times psi. And this is the probability that you obtain the outcome, measurement outcome, lambda mu. Okay? And finally, once you have done the measurement, the state of your system has not changed. And this is the irreversibility part. The state of your system has been changed. And how was it changed? It has been projected along the direction which is given by the measurement result. So if you have measured lambda mu, then basically you take the state, initial state psi, you project it along this eigenspace, p mu of psi, and you renormalize it. And so your new state is going to be given by this. And of course, as this is a projection, this is irreversible. So it means that now, if you start from the state psi plus, there is no way you can go back, find back psi, because you have projected in a smaller space because of the measurement result. So these are basically the three features, main features, that if you can understand, then you can basically model any quantum system. And at the same time, that explain the richness of the quantum mechanics with respect to classical mechanics. Why do we have these new applications that are used here? So I'm not asking you to understand all of these very well now, of course, except I guess if you have had quantum physics courses, then these are maybe natural. But it's not very important that you understand them precisely here, because my talk is going to be much more, I would say, popularization. From now on, it's going to be less of math, I guess. So, except maybe towards the end if you have time. Okay, so what is a quantum bit, or quantum bit of information, or a qubit, what we call a qubit in a quantum computer? Basically, is a physical system with two possible states. So it's 0 and 1. I show them, we use this notation of ket 0 and ket 1. Well, this is just some physicist notation to simplify calculations, but don't worry about it. So you can think of 0 as apple and 1 as oranges. So if you want C0 times apple plus C1 times orange, it doesn't matter what they stand for. It's basically the 0 is the vector 1, 0, and 1 is the vector 0, 1, if you want. So basically, the state of your system is a vector in C2. C to the power 2, because C0 and C1 are complex numbers. And then the norm of C0 squared plus C1 squared should be 1, which is what I told you before, which means that the state of the system lives on the unit sphere of its Hilbert space. Here, the Hilbert space is simply C2. So in the case of a qubit, we have a two-dimensional Hilbert space, and we live on its Hilbert, which is C2, basically. And then we live on its unit sphere. So what happens now if we have many of these qubits? So this is, of course, in the case of a classical bit, you know that you have either the state 0 or 1. Here, what we say in the case of the quantum bit, we have the possibility of having all these superpositions of 0 and 1. So what does it change with respect to classical case? It's just that now if you consider many qubits, so for example, n qubits, you have 2 to the power n possibilities, right? So you have all the combinations of zeros and ones that you can imagine, so the 2 to the power n of them, and you have all the coefficients in front of them. So basically your state is now a superposition of this form. And this is what we call, so when I say 0, 0, 0, 0, it's basically meaning, it means, mathematically, it means 0, tensor 0, tensor 0, tensor 0. But you can just consider it as now the new elements of your basis are these 2 to the power n elements. And you have all the coefficients that you could have here. So you're in the unit sphere of this 2 to the power n dimensional space, Hilbert space now. Okay, so in the case, again, I recall you, in the case of the classical bit, you had one of these possibilities. You were in, you could say, the state of your, let's say, quantum, the state of your computer at, or your circuit, basically, with n bits at the time t is given by 0, 0, 1, 0, 0, 0, 0. Here we have, at the time t, we have all these possibilities with coefficients which appear in front of them. Okay. No, okay. Why this is powerful? Does this give us? We have this kind of quantum parallelism. So basically, if you know a way in a classical algorithm to compute the function which sends a binary vector of dimension n to a binary vector of dimension m. So basically, you have a circuit which calculates this function f from a binary vector of dimension n to the binary vectors of dimension m. Now, what we can do is that we can also engineer a quantum circuit that maps basically any vector x. So this new basically this vector is now replaced by these wave functions or these states, if you want. The vector x here is a vector of dimension n, and the vector 0 here is a vector of the zeros of dimension m. So basically now this classical algorithm can be replaced by this quantum circuit, which sends x0 to x f of x. Okay, and knowing that f of x is another vector, another binary vector in zeros and ones. So, okay, this is nice because now if you come and apply this same quantum circuit to a superposition state of this form, so a state which has all the possible x states in it, then at the end what you get is the new state is x f of x. So basically you have, just by applying your quantum circuit only once, you have calculated the value of your function at all its inputs. That's the strength of the quantum. Where the strength, we'll see that in a bit, that this is actually we have to be careful about this reasoning. This is not as nice as it appears. Things are harder actually. But just I should mention something that I forgot. So the entanglement here is that these states cannot necessarily be written of the form of separable tensor products. For example, if you have the state 0, 0 plus 1, 1, there is no way you can write it as a tensor product of a state of the first qubit times the tensor product times tensor product with the second of the second state. You see, because 0, 0 plus 1, 1, you cannot write it, for example, as 0 plus 1 times 0 plus 1. So it's an entangled state. If the first qubit is measured in 0, the second one is necessarily in 0. And if the first one is measured in 1, the second one is necessarily in 1. Okay, so this is basically this concept of entanglement. And so basically what we say is that now using this quantum circuit, which actually can be modeled by this unitary operator as a linear unitary operator acting on your system, directly you have the result of your calculation for all input values with a single run of your circuit. However, as I mentioned, there is something to be careful about. There's something to be careful about. And the first thing is that we cannot measure this total state. In fact, the quantum mechanics does not allow us to measure the wave function of your system. So you cannot know these values altogether. What you can do, and this is basically because of this principle, that the third principle that I mentioned to you, the fact that you can only measure observables which are of this form. And basically, you cannot measure two observables which do not commute with each other, for example. So for example, if you have two operators that do not commute with each other, then you cannot measure them. So which means that basically you cannot measure the whole state at the same time. You can only have, so the whole art, I would say, of the quantum computer science is to find the good ways of measuring things, or good observables to measure on this final state that you see here, to retrieve some useful information, much faster than a classical system. Okay, so that's what a computer scientist who works in quantum algorithmics tries to do. But that's not my job. So our job, basically, in our group is more about this second issue that you see here. The above lemma that I mentioned here, which says that for a classical circuit could be replaced by a quantum circuit which does this calculation for you, is only valid if your qubits are perfect. basically, which means that if you can, your quantum operations, logical operations, can be performed precisely on your system in an exact manner. In the case where you have errors on these logical operations, unfortunately, this is not anymore true, and we cannot realize necessarily this circuit, and that's what we call the hardware bottleneck. So, and that's where we that's where our activity in our group is.
Pardon, sorry for my interruption.
سوالتون هم میتونی به فارسی بپرسید. ببخشید من فقط مشکلم دارم.
اوکی. یکی از بچه‌ها سوال پرسیده که is it true that quantum Bogo sort has O1 complexity؟ میتونی بگید.
آره. سوال دقیق فکر کنم نفهمیدم شاید، ولی is true that quantum Bogo sort has of n complexity. Bogo sort, is that فکر مطمئن نیستم بدونم چیه Bogo sort.
میتونید میکروفونتون رو روشن کنید آقای وایس؟ من شما میکروفونتون رو روشن کرده بودم. بزنید یه بار دیگه میکروفونتون رو روشن کنید.
سلام. والا یه الگوریتمی که هست کوانتوم بوگو سورت، کلا بوگو سورت اینطوریه که همه یه جایگشت ها رو میاد ایجاد میکنه، یعنی میگه که یه جایگشت به تصادف ایجاد کن، بعد ببین که این سورت شده هست یا نه. بعد میگه که خب یه جای اگه سورت شده هست که خب فبه حل مراد، یعنی دیگه اوکی. اگر نیست بیا یه جایگشت دیگه ایجاد کن، دوباره به همین صورت. بعد خب کوانتوم بوگو سورت میگه که خب همه یه جایگشت رو بیا ایجاد کن و ببین که آیا سورت شده توشون هست یا نه، کدوم سورت شده هست. بعد اینطوری من یه جا خوندم که این درست نیست، یعنی استدلالش درست نبود.
راستش خب اینو من تو خواستم بگم، ولی توی این الگوریتم سورتینگ یعنی گروول الگوریتم گروور هستش که الگوریتم کوانتومی هست که نشون میده که از O of n به O of square root of n که اون ولی چیز این برای وقتی که میخواین چیزو در واقع یه دفترچه تلفنی رو بخواین برای سورت کردن یه دفترچه تلفنه در واقع، ولی بوگورت سورت همین چیزی که میگید مزرونه که یه بدونید. فکر کنم مسئله که شما دارید میگید الگوریتم دو جزا رو دارید در موردش صحبت میکنید شما احتمالاً، که میگید که من میدونم که یه دونه در واقع الگوریتم دو جزا چی بهتون میگه. الگوریتم دو جزا به شما میگه که شما در واقع یه دونه جایگشت هستش که به فرض جایگشت درست هستش و میخوایم اون رو بدونید. یعنی در واقع توی اینجا توی اگه برگردم توی این اسلاید که داشتم نشون میدادم، الان اسلاید من میبینید درسته؟ توی این اسلاید یعنی در واقع جواب تمام ایکس ها صفر هست غیر از یکیشون، یا غیر از یکی از ایکس ها که یک هستش. در واقع مسئله اینه که حالا آیا میتونم اون ایکس رو پیدا بکنم که جواب اینجا یک هستش یا نه. مسئله به اینه. با چند تا سوال کردن از این سیستم من میتونم اینو بفهمم. البته همه اینا رو باید یه مقداری با چیز کرد. این درسته، این با یک بار میتونید چیز کنید، ولی مسئله مشکلی که هستش اینه که همه این کد کردن این اینفورمیشن در داخل این استیت، این کد کردن در واقع مسئله اوراکل هستش که همیشه وجود داره توی این سیستم. این کد کردن اینفورمیشن اولیه توی چیز ممکنه که خود اون زمان بیشتری ببره بخواد تا O1. این اینتروگیشنش یاد O1 باشه، ولی این کد کردن اینفورمیشن O1 نیست. خب به هر حال من میگم اصلا به هیچ وجه اکسپرت توی فیلد کوانتوم الگوریتمیکس نیستم، میگم کار من بیشتر قسمت فیزیک جریانه. فقط خواستم برای این کسایی که حالا من اصلا بدونم که خب برای چی این کار رو ما میکنیم، بگم که این در واقع این قسمت این قدرت فیزیک کوانتومی از اینجا میادش، ولی حالا خود این فیلد یه فیلد خیلی اکتیوی هستش و خیلی آدم زیادی تو قسمت کامپیوتر ساینس رو این کار میکنه. خب حالا در مورد این من همونطور گفتم کاری که ما میخوایم بکنیم الان بیشتر مربوط به این physical realization در واقع sorry I'm gonna talk more about the physical realization of these qubits. So there are many platforms that people use to do this, that people consider to perform this. So one of the most advanced ones is the trapped ions. So basically we have these ions that you see here actually that are trapped and which are manipulated with laser fields individually. And then this internal, basically each qubit is the internal state of one of these ions. And then basically the
ببخشید دوباره میتونید اون لیزر رو بزنید.
آها
مرسی.
بله این ترپ هایی که داشتم توضیح میدم اینجا هستن. یکی از پلتفرم ها اینا هستش، پلتفرم های فوتونیک هست، مدارهای فوتونیک که در اونجا در واقع کیوبیت ها در مثلا پولاریزیشن فوتون ها میتونه انکد شده انکد شده باشه، or it can be the spin qubits or superconducting circuits. So what I'm going to talk about today is mostly about these superconducting circuits because these are our this is the field I'm working in. Okay, so what is quantum about this system? So you can consider this LC circuit, so an inductance in parallel to a capacitance. Okay, so if you consider this LC circuit and you consider like the ensemble of electrons or the electronic condensate which oscillates, so you know LC, circuit is called an LC oscillator. If you, I don't know whether they're also, you have had, I guess, courses on this before, of course, at high school even. So the LC, this electronic condensate oscillates around this positive ionic crystal in the same manner as the single electron of a hydrogen atom oscillates around basically the nucleus of the hydrogen. The only thing that changes is the scale. Here we are working with a very small system with a very little mass, small mass. So basically the size, the level of angstrom. Here we're working with circuits which have a size of a millimeter. So what we can ask ourselves is, what is then quantum about the system this big? It's a macroscopic system. It's a system we see with eye, naked eye. So how can we think that this system is actually quantum? Well, the thing is that the most important question is actually temperature. It's not much the size of the system that says to that, and the temperature and the frequency of your system. So if this is an oscillator and this is an oscillator. This oscillator has a much higher frequency than this one. Actually, the frequencies that we work with, so the LC oscillators that I will be working with, have frequencies in the range of 5 to 10 gigahertz. So this is what we call the microwave regime. And in this microwave regime, basically, you go in the quantum regime when you reduce the temperature below some value, which is given by about 1 Kelvin. So here, when you're in 20 millikelvin, you are deep in the quantum regime, basically. So this is basically coming from the Boltzmann law. Okay. In the case of a hydrogen atom, the frequency is much higher, and at room temperature, 5 orders of magnitude higher. So at room temperature, basically, you're already in the quantum regime. This is just the only thing that changes. So basically, if you increase the temperature of a hydrogen to many, many kelvins, then you are also going to get out of the quantum regime. But basically you're gonna ionize it, so you cannot then talk about this electron, which is if you give it too much energy. So here we're gonna be working with these circuits, but which are at very low temperature, so that we can use the laws of quantum physics. And so then what does the laws of quantum physics tells us here? It tells us that now if you consider the magnetic flux in this inductance and the charge on this capacitor, these two variables become quantum variables, just similar to the position and momentum of a hydrogen atom. They become basically conjugate physical variables. And so now you can write the Schrödinger equation to basically model the dynamics of this system with a wave function, and the Hamiltonian is going to be given by this operators q squared over 2 times capacitance plus phi squared over 2 times inductance. What are these two operators q and phi? Well, the operator q is the derivative with respect to phi, and the operator phi is the multiplication by phi, by small phi. So basically you have now a wave function psi. If you want to go back to the first slide that I had here, your Hilbert space is a space of L2 functions on phi variable. And so you have all functions with a variable as variable phi. And what I'm telling you is that now my Hamiltonian, which is a Hermitian operator or a self-adjoint operator, is the second derivative with respect to phi plus phi squared over 2. Okay, so this is what how one can model an LC oscillator in the quantum regime. You know that in the classical regime you have just the dynamical system of a harmonic oscillator. So basically it's phi double dot equals to minus 1 over LC phi, right? If you don't have any resistance, then this is just phi double dot equals to minus phi with some minus some omega squared phi, and omega squared here is given by 1 over LC. Okay, so if you look at this Hamiltonian, basically this Hamiltonian, and you look at its spectrum, you diagonalize it, you're gonna see that you have these eigenenergies which are all equidistant. So the fact that it's a harmonic oscillator means that these energy levels are going to be all equidistant from each other. And this frequency omega r is given by 1 over a square root of LC, L times C, basically. Okay, so h bar is the Planck constant. Okay, so this is basically telling you that if you wanted to use this system, if you wanted to write the dynamics of this system, basically you should write I psi dot, where psi is a function of phi, equals to minus 1 over T2C, second derivative with respect to phi of psi, plus phi squared over 2L phi. So you have psi. So you have basically a PDE, a Schrödinger equation, which models this LC oscillator. Okay, now LC oscillator is a harmonic oscillator, and unfortunately we cannot use it as a qubit, because if you, as I told you, a qubit is a 2-level system. Here you see you have an infinite number of levels, and unfortunately you cannot really separate any two of these levels from the rest of these levels, because each time you want to, for example, come and excite your system from this level to this level, you can do it with a microwave drive, basically with a field. Electromagnetic field at this frequency, but then this frequency is the same as this one, so you're going to start to populate all the other energy eigenstates as well. So basically you cannot really isolate 2 levels from the others. This is why instead of using a regular LC oscillator, we use a nonlinear LC oscillator, if you want, where basically we replace the inductance with something which has a nonlinear relation between current and voltage. And this is the famous Josephson junction that I talked to you about at the beginning of the talk. So what is a Josephson junction? It's 2 electrodes, superconducting electrodes, which are separated by a very thin layer of insulator. Typically, in our case, in our experiments, this is 2 electrodes of aluminum, which are separated by a nanometer of aluminum oxide. So basically, you prepare one first layer of aluminum, you let it oxide on the top, on its surface, and then you put another layer of aluminum. And that's how you make one of these Josephson junctions. And this is basically going to be replacing this in nonlinear inductance. This is basically was a very important result from the mid-20th century, that this system can be seen as a lossless nonlinear oscillator, nonlinear inductance. Something like a diode. A diode is a nonlinear device, but it's lossy. Here, Josephson junction allows you to have a nonlinear element which is not lossy. And what happens is that then this potential phi squared over 2L that I mentioned is now going to be replaced by some cosine of phi, if you want, because of this Josephson junction. So basically, it's like a pendulum. You know that if you want to write the potential of a pendulum, you have a cosine of phi, right? So the Josephson junction is very similar to a pendulum. You know that a pendulum is a nonlinear oscillator, whereas a spring, for example, is a linear one. So we can actually, these are all approximations, of course, but so the potential of a Josephson junction is just similar to a pendulum. So what is interesting now is that now if you look at the eigenvalues of this operator minus second derivative with respect to phi, or minus Laplacian, plus cosine of phi, then the eigenvalues are now not anymore equidistant. They are different in energy and different in the transition frequencies are different. And so now if you come and, for example, apply a drive only at this pink resonance frequency, then you're going to only excite the system between this first level, ground level, and the first excited level. You're never going to populate, or at least with a very good approximation, you're not going to populate the higher levels. So we can really talk now about a qubit. We can separate two energy levels from the others. So this is how most people are trying these days. A lot of people trying to these days to make quantum computers using these kind of circuits. So this is basically what Google uses in their experiments, what IBM uses in their experiments, and most recently Amazon as well is working on that, and many academic actors around the world, of course. So this field of basically quantum superconducting circuits started somewhere around 2000. So the first qubit was realized in 1999. And it had what we call in a lifetime of about nanosecond. What's a lifetime? It's basically how long your system preserves its quantum superposition states. Basically, if you put it in the state 0 plus 1, to what, how much time it remains in this state 0 plus 1 before jumping to either 0 or 1. So it's, you know, if it's either 0 or 1, it's a classical bit. Now we want to preserve these superposition states. So how long can we preserve it? This is what we call this coherence time or lifetime of a qubit. And in the very early days, this has a very short lifetime of about a nanosecond. And this is mainly because, well, we have a very macroscopic system, very large system, which interacts very strongly with its environment. So this is basically what creates what we call a decoherence, and which basically removes the coherence or removes the superposition of the two states. Basically, it's like your environment is measuring your qubit. It's asking whether you are in the state 0 or 1 and projecting it in a random manner towards 0 or 1 without letting remain in this superposition state. Okay, so over the years, this has been improved very significantly. So basically by 5 orders of magnitude in the past, I would say 20 years. But actually, I could say that from 2010 or 12 on, that we haven't seen that much of a change. You see, it's about at most 1 order of magnitude, but even not that much. It oscillates. So we have had different ways of realizing these circuits. that allowed us to basically bring it to this 5 order of magnitude improvement over the years. But at some point it stopped. Well, first reason for why it stopped is because over these basically 10 years or 12 years, people removed all the more obvious problems. And of course, now we get to the level where we should work harder to improve these coherence times. But then another reason is that we are in this 10 to the power 2, so about 100 microseconds, is maybe enough to start doing something else, which is called quantum error correction. Okay, so that's why, from here on, people thought, let's stop now and try, or not stop, let's maybe now try to invest something else as well, try to make from these faulty qubits something which might be less faulty. Okay. So just to fix the idea, these values that we have these days, basically the best values that we can have these days, leads to this basically figure of merits that you see over here. So we can know these days we can perform single qubit logical gates with a precision of about 1 per 1,000 in this field of superconducting circuits. So which means that if we perform 1,000 single qubit logical gates, one of them there has an error. Okay, this is a probability, of course. And then to 2 qubit gates of 5 per 1,000. And this is basically not far from what we call the threshold for quantum error correction, as you will see later. But just to fix the ideas as well, for example, for the Shor factorization algorithm, which is one of the most known algorithms, quantum algorithms, we need gate errors in the order of 10 to the power minus 15. Okay, this is very, very far off. You see, you have 12 orders of magnitude to win here. So what is the Shor factorization algorithm? It's an algorithm, a polynomial time, that allows you to factorize large numbers. As you know, this is a hard problem. At least we don't know a polynomial time algorithm and for a classical computer. In the quantum case, we can have this exponential speed up through this Shor's algorithm. But it requires a lot of qubits, basically. And so it means that very precise gates operations. And so how can we overcome this gap of 12 orders of magnitude? We could hope, especially that we don't believe that we can just improve physical systems and keep increasing this to 10 to the power minus 15. We should be more intelligent about it. And this is the idea of quantum error correction. So before explaining what is quantum error correction, let me explain what is classical error correction. Because classical error correction exists and is used, for example, in your cell phones is used. So you know that if you have a classical bit, so which takes a circuit which takes either the value 0 or 1, it's a switch, basically it's on or off. If you wait some time, there is a chance, there is a small, maybe it's very small, but there is a probability that it jumps. So there is an error, there's bug, and this 0 basically becomes a 1, or 1 becomes a 0. Sometimes this error comes because you wanted to do an operation, and so you wanted to intentionally bring it to 1, but you brought it instead to 0. This is an error of your gate, basically, as well. But I mean, here let's consider we are just looking at identity. We wanted to stay in 0 or 1, but if we have waited some time tau, 1 second, and this time in this time of 1 second, with some probability p small, it might have jumped to 1, or vice versa, from 1 to 0. So the idea of classical error correction is use the redundancy. So basically encode 1 bit of information in more than 1 bit, more than 1 physical bit. So we talk about logical bits and physical bits. So encode 1 logical bit in maybe 3 logical bits, for example. So replace 0 by 3 zeros and 1 by 3 ones. So why is this interesting? Because now, if we wait the same amount of time of 1 second, for example, with the probability p, one of the bits is going to jump. Well, with the probability 3p, actually, one of the bits is going to jump. Okay. the probability that 2 of the bits jump is of order p squared. Okay, but if you come at the end of this 1 second and you measure your bits, you do a majority vote. You ask, am I in the do I have more zeros or do I have more ones? If I have more zeros, then I say I'm in 0. If I have more ones, then I say I'm in 1. Then you see that, well, you have actually basically corrected the error. And you have now the new errors are of order p squared, because if, of course, if you had 2 of your bits that had flipped, then by this majority vote you're making a mistake. So, but this is of only p squared. So if p is small, you see that you're going to win. If you want to go to even higher order p cube, you can use 5 bits instead of 3 bits, for example, and do a majority vote, and etc. So this is, of course, the most basic error correcting code that exists for the classical systems, for the classical bits. This is called the repetition code. And the idea is that in the case of quantum, we can do similar thing, but it's more complicated. What is going on is that, well, as I told you, you want now to basically preserve all these superposition states. You don't want to preserve only 0 or 1. You want to the capability of keeping all these states C0, 0 plus C1, 1 without knowing what C0 and C1 is, because basically the C0 and C1 can be anything. Okay, the first thing is that, well, instead of using 3 0, you can still use 3 zeros and 3 1s, but the new state is now going to be an entangled state. So it's basically C0, 0 tensor 0 tensor 0 plus C1 tensor 1 tensor 1 tensor 1. Okay, so this is not bad. Maybe it's hard to prepare these entangled states, but this is not a big deal. I mean, we'll overcome it at some point. But now we should still be careful. You cannot, for example, come and do majority vote. If you ask your bits if they are in 0 and 1, basically you're gonna break this superposition state. This is the third property of quantum systems that I mentioned at the beginning. I told you that if I measure some observable, I'm gonna project the state along one direction. So if I ask my system whether it's in 0 and 1, it has to decide whether it's in 0 and 1. It cannot remain in the superposition state. So basically, you cannot ask your system, do you have a majorities of 0 or a majorities of 1? You cannot measure it. It's not compatible with the state. What you can do is do what we call parity measurements. So you can ask the qubit number 1 and the qubit number 2, do you have the same state or not? You see that the response to this question now is yes or no, but it doesn't break this superposition. Basically, if there has been no error, the state of the first system and the first qubit and the second qubit is the same. So whether it's 0 or 1, it's the same. So it's it doesn't have to decide whether it is in the blue part or in the pink part. It just has to. He just tells you yes. My parity is 1. Whereas if the first qubit had jumped, so this 0 had become 1 and this 1 had become 0, then the parity measurement would have given 1 still without breaking this superposition. Basically, -1. Basically, this parity would have given you that parity is different, is odd. Even though this position would not break. So basically what you need to do is something more subtle. You cannot measure the qubits one by one. You have to measure their parity. Basically, you have to measure whether they are in the same state or not. This is not easy. Basically, you don't absolutely want to avoid measuring the bits the single qubits. You want to measure their common properties, basically. And then you just measure the parity of the first qubit and the second qubit, and the parity of the second and third qubit. And you have 4 outcomes, either plus plus, minus plus, plus minus, and minus minus. If plus plus, it means there is no errors. Minus plus, it means that qubit number 1 has flipped. Plus minus means that qubit number 3 has flipped, and minus minus means that qubit number 2 has flipped. So this is the way you can correct then your errors. Okay, this is just part of the story. In fact, things are still a little bit more complicated. What you can, in fact, in quantum systems, you can have all sorts of errors. Basically, you don't have only bit flips. So basically, this superposition state C0, 0 plus C0, C1, 1 could either jump to the, I mean, basically what has happened is that Peter Shor in the 90s and then 95 demonstrated that if you correct for one of these 4 possibilities, then you correct for all possible errors on the qubit. Okay, so what are these 4 possibilities? So either nothing, identity, so 0 remains 0 and 1 remains 1. Either bit flip, which is the similar thing to the classical systems that we had before, so 0 becomes 1 and 1 becomes 0. Either phase flip, which means that 0 becomes 0 and 1 becomes minus 1, so which means that there is a minus sign here. Either a bit flip and a phase flip. So basically, 1 becomes 0 becomes 1, and 1 becomes minus 0. So that you end up in this state. So if you want to do a full error correction, a quantum error correction, you need to correct for all these possibilities of errors. So this means that you need more qubits. In fact, one of the most common approaches that is used, for example, by companies like Google and IBM, is to use this what is called surface codes. So surface codes is what replaces this repetition code I mentioned to you for the case of a classical system. So the repetition code is maybe one line of these qubits, if you want, where you were measuring the ZZ parities. So it's parity along one direction of your qubit. And then the idea of surface codes is to have then a whole patch of these qubits where you perform all kind of parity measurements between 4 by 4 of these qubits in different bases, and then you correct these errors. So these are errors in phase or in bit flips or phase flips that are correct. So these surface basically corrects both types of errors. Bit flips, phase flips, and bit flips and phase flips. The only problem is that, well, it's very hardware consuming. So first of all, I told you that this thing, well, of course, if you have a single qubit which doesn't have very good properties, if you put many of them together, it's not necessarily going to solve your problem. It's going to solve your problem only if each of the qubits is good enough. Okay, so for example, how to understand this? I told you here that P, that this is of order P squared. Actually, what is there is a constant in front of P squared here, and this constant is much larger than 1. If your P is smaller than 1 over this constant, which is in front of this proportionality, and this proportionality constant, then you're going to win by using this repetition. If this P is larger than that 1 over that constant, then of course you're going to lose, because C times P squared, if C is huge. For example, imagine that this C is 1,000. Okay, why is this big? I'm not going to go into the details of that. But let's say you have 1,000 here. If your P is less than, if your P is more than 1,000, then 1,000 times P squared is still larger than P. So it would have been better not to use this code. It's only interesting if P is smaller than 1 over 1,000, 1 over that constant. And that's what we call the threshold for error correction. It appears that for this surface code, the threshold is somewhere around 0.5% for logical gates that are used in these measurements. So, and that's, I remind you, I told you that we are basically about 0.5% for these 2 qubit gates. So we are just barely at the point where we can start to do error correction. Below this point, if you increase the size of your patch, your surface, the probability of logical errors will decrease exponentially with the number of qubits. So you see, for example, if I use d equals to let's say 7, which means that I have a 7 by 7 patch. There's 49 qubits, actually times 2, because you have there are two types of qubits, so about 100 qubits. You go from 10 to the minus 3 error level to 10 to the minus 5. You see that, well, and of course,